Salam and peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning together. There is one field called phi, spelled Phi. Phi is the holophase, a cyclic rhythm defined at every point in the universe. Its first derivatives give three simultaneous echoes. Time, which we call omega, spelled Omega, space, which we call k, and motion, which we call v, built from both omega and k. Above them, higher derivatives form a branching tree that in principle goes on forever. Every law of nature is a pattern in this tree of derivatives of phi. Today, we zoom into just one branch of that tree. In part 12, we stood inside the pulse of time. We met omega as the local ticking rate of reality, the way phi turns in time at each point. We imagined the universe filled with tiny invisible clock hands, each one spinning with its own tempo. We learned that what we casually call time can be understood as a landscape of local cadences. Where omega is larger, the local rhythm is fast. Where omega is smaller, the local rhythm is slow. We also opened the doorway into falsifiability. We said that if the holophase model is right, different physical clocks in the same place are not just coincidentally in sync, they are all reading the same underlying omega field. If careful experiments ever show that no such common cadence exists, the model must be revised or abandoned. Now, in part 13 of episode 6, we turn our attention from the pulse of time to the weave of space. If omega is the way phi changes when you nudge reality forward in time, then k is the way phi changes when you nudge reality sideways in space. This part is called the weave of space, k, the spatial pattern. Our goal is to make k so intuitive that you can almost feel it under your feet as you walk, and at the same time keep it sharp enough that a physicist with a notebook could translate everything back into equations. As always, what you are hearing now is the gentle, story-based layer of the Holophase program. Underneath it lives a rigorous layer, more than 30 scientific papers where phi and its derivatives are defined precisely. 4 of those core papers are already printed and archived on Zenodo, so that anyone in the world can read them, criticize them, and test them. The Holophase audio series is built on top of that foundation. It is not a replacement for the mathematics. It is a bridge into it. Let us begin with an image you already know well, a landscape of hills and valleys. Imagine you are standing somewhere in the mountains. If you stand on a perfectly flat plateau that stretches out in all directions, you feel no pull toward any particular side. You could walk north, south, east, or west, and at first nothing about the slope would change. That is a place where the gradient of height is 0. Now imagine you walk to the side of a hill. Suddenly your body knows which way is down. If you let a ball roll from your feet, it will choose a direction. The steeper the slope, the faster the ball picks up speed. Here, there is a clear gradient. Height changes as you move across the ground, and it changes in a particular direction. In this picture, height is like phi's value, and the slope of the hill is like k. The gradient tells you, at each point, how quickly something changes if you move a little, and it tells you in which direction that change is steepest. In ordinary physics classes, people talk about the gradient of a scalar field. In the Holophase language, we say k is the spatial gradient of phi, the way phi varies across space. For an audio listener, we can say it even more simply. K answers the question, if I walk a tiny step from here, how much does the phase change, and in which direction does it change the most? To make this concrete, imagine the universe filled with tiny arrows again, as we did in earlier parts. At every point in space, there is a little arrow pointing somewhere around the circle. That arrow represents the local value of phi. Now, freeze time completely. omega goes quiet. Nothing moves forward in time, we take a snapshot of the universe. You begin to walk through space and watch how those tiny arrows change their direction from place to place. If you walk through a region where the arrows all point almost the same way and only tilt very gently as you move, then the spatial pattern is smooth. Phi is changing slowly from point to point, and the magnitude of k is small. If you walk through a region where the arrows spin wildly as you take even a tiny step, then the spatial pattern is tight and intricate, and the magnitude of k is large. The vector k at your starting point points in the direction where the arrows change the most when you move, and its size tells you how strong that change is. You can think of it like texture. Look at the wallpaper in a room, or imagine one if you cannot see it now. A plain white wall has almost no visible pattern. If you move your eyes across it, the color and brightness hardly change. That is a region of small spatial variation, small k. Now imagine wallpaper with dense stripes or tiny repeating floral patterns. As your eyes move, the scene changes rapidly. Light, dark, light, dark, leaf, flower, leaf, flower. That is a region of large spatial variation, large K. The direction of the stripes or the flow of the pattern matches the direction of K. Your visual system is constantly reading these gradients without knowing the word K. Water gives us another beautiful analogy. Picture the surface of a lake. On a quiet day, the waves are long and gentle. The distance between one crest and the next is large. As you move across the water surface, height rises and falls slowly. That is a small K pattern. On a stormy day, the waves are short and choppy. Crests and troughs alternate every few centimeters. Now, as you move, height changes rapidly over small distances. That is a large K pattern. If you drew little arrows perpendicular to the wave crests, pointing in the direction the pattern repeats, those arrows would give you the direction of K. The tighter the spacing of the crests, the bigger the magnitude of K. Scientists often talk about wavelength, the distance between two crests, and wave number, which is essentially how many crests fit into a given length. The wave number is closely related to the length of K. In the Holophase language, we treat K itself as the primary object, a vector field telling us, at every point, how quickly the phase is changing in space and in which direction. Wavelength and wave number become different ways of reading K in a particular situation. Let us return once more to the rug weaver, because this image is central to the entire Holophase language. Imagine a master weaver at a loom. Threads run vertically, forming the scaffold of the rug. The weaver ties colored knots, row by row, building up patterns. In some parts of the rug, the pattern is simple and broad, large shapes that stretch across many centimeters. If you move a finger across that region, the colors change slowly. That is a small K region. In other parts, the pattern is incredibly fine. Tiny flowers, detailed geometric designs, different colors packed tightly together. If you slide your finger there, the colors change every millimeter. That is a large K region. Now, pay attention to direction. Perhaps the motifs repeat diagonally, a line of little diamonds climbing upward to the right. If you move your finger along that diagonal, the pattern changes quickly. If you move perpendicular to that diagonal, maybe the pattern hardly changes at all. The direction in which the pattern changes most rapidly corresponds to the direction of K in that piece of the rug. The Holophase story says, space itself is like that rug, but made of phase rather than threads. Phi is the underlying color, defined on a circle rather than a palette. K is how that phase color changes across the fabric of space. Where the phase weave is tight, K is large. Where it is broad and smooth, K is small. Underneath these pictures, there is a very compact mathematical sentence. In the formal papers we write, K equals minus the gradient of phi with respect to space. For everyday speech, we can strip this down. K is the spatial derivative of phi. It is the list of numbers that tell you how phi changes when you move in each independent direction of space. Because we are in an audio journey, I want to read this slowly as a kind of spoken formula. Imagine I am writing it on an invisible board as I say it. K is equal to the spatial gradient of phi. That means, take phi, look at how it changes when you move a tiny distance in the x direction, a tiny distance in the y direction, and a tiny distance in the z direction. Collect those three rates of change into one arrow. That arrow is K. You do not need to remember any symbols to hold the meaning. Anytime you hear K, think how tight and in which direction the phase pattern is changing in space. Now, just as we did with omega, we should ask, how does this become physics and not just language? Where does falsifiability live here? The Holophase framework makes a clear claim. All spatial structure in physical fields can be rewritten as patterns of phi and its spatial derivatives. That means that whenever you see a stable pattern in an experiment, an interference fringe, a standing wave, a diffraction pattern, a lattice of atoms, even a pattern of light in a microscope, there is a corresponding K field that describes how the underlying phase changes in space. If that is true, then different systems that read that same K field should see compatible patterns, even if they are built in very different ways. Here is one way to test this claim, spoken in plain language. Imagine a laboratory bench with three separate experiments on it. On the left, a laser passes through a double slit and produces bright and dark fringes on a screen. In the middle, a beam of electrons passes through a similar double slit and paints an interference pattern on a detector. On the right, a carefully built mechanical membrane vibrates with a pattern of peaks and nodes, like a drumhead with a beautiful standing wave. In ordinary physics, we explain each of these systems with its own equations. Maxwell's equations for light, the Schrödinger equation for electrons, and elastic wave equations for the membrane. In the Holophase description, we try to describe all three in terms of one underlying phase field phi and one spatial derivative field k. If the autophase model is right, then when these experiments are arranged so that they probe the same underlying spatial structure, for example, they are built on the same pattern substrate or they feel the same effective phase landscape, there should exist a single K field that makes sense of all three patterns at once. The relationship between fringe spacing, node positions, and phase twists should fit together as different letters written in the same underlying language. If extremely careful experiments show that no such common K description is possible, that you cannot, even in principle, reconcile the spatial structure seen by light, electrons, and mechanical waves into a single phase gradient field, then the holophase framework would be in serious trouble. That is falsifiability. It is not enough that we can tell a pretty story. The patterns must line up in the numbers. The Zenoda papers begin to spell out such tests in more formal terms. They take known wave experiments and rewrite them in holophase variables. They show that in well-tested regimes, the new language reproduces classical predictions. That earns the theory the right to be considered. But they also point toward new regimes where different waves interact in the same structured medium and where a common phase and K description can be tested. That is where the holophase model rises or falls. Now we deepen this picture even more. Today, we simply name space's first basic letter, K. This also sharpens what we mean by structure in the holophase view. In older language, people often talk about energy as if it were a kind of fluid that gets poured into different containers. In the holophase model, energy is not a mysterious substance. It is a careful tally of how phase patterns are arranged and how they change. K contributes to that tally, but it is not energy in the old picture. It is one of the fundamental descriptors from which the accounting is built. You do not need the formulas now. It is enough to feel that when physicists in this framework talk about how much is happening in a region of space, part of what they are really counting is how strong and how directed are the phase gradients here. And that is exactly what K captures. Let us gift ourselves one more experimental picture, because falsifiability is the heartbeat of this whole journey. Imagine a plate drilled with a repeating pattern of tiny holes. When you shine light through it, a delicate lattice of bright spots appears on a screen. When you ripple water across an array of pegs in the same pattern, you see standing ripples form in some regions and stay absent in others. Standard physics uses different tools for these systems. The holophase language says, beneath both, there is one shared spatial phase pattern and one shared K-field sculpted by the drilled holes or the pegs. The plate is not just matter. It is a device for shaping K in space. This idea leads to a sharp test. If two or more kinds of waves pass through the same carefully designed pattern, and we measure their spatial structure with high precision, we can ask, is there a single K-field that explains all of them at once, within experimental accuracy? The holophase model predicts that the answer should be yes, up to known corrections, because the spatial phase gradient is a common resource that different waves sample in different temporal ways. If refined experiments, controlling all other influences, repeatedly find that no such common description is possible, that each family of waves sees a fundamentally incompatible spatial structure, then the holophase model would be in real trouble. K would not be the universal spatial letter we claim it is. That is exactly the kind of risk a serious theory must be willing to take. To bring K even closer to your senses, imagine closing your eyes and running your hand along two different surfaces. A smooth table, finely sanded, offers very little surprise as you move. Your palm glides with almost no change in pressure. A rough stone wall offers constant micro surprises. Tiny ridges, shallow dents, grains of sand sticking out. Your skin is sensitive not to the absolute height of each point, but to how height changes between neighboring points. It is a gradient detector. At this tactile level, your nervous system is already acting like a little K-meter. In future parts of episode 6, when we speak about knots in the phase fabric, about curvature, and about forces, K will keep returning. Defects will often live where K and its cousins cannot be made smooth. Curvature will describe how K itself bends and loops. Effective forces will be seen, in part, as the way systems respond to structured K landscapes. By meeting K clearly now, as a simple measure of how phi changes across space, you are preparing yourself to recognize its face when the grammar of the language becomes more elaborate. If all of this feels abstract, remember that at its heart, the idea is very simple. Take any pattern you like: waves on water, tiles on a floor, leaves on a branch, lights in a city at night. Notice where the pattern is tight and where it is loose, where it changes quickly and where it changes slowly. That noticing is the doorway into K. The holophase model then makes a bold, testable claim. Beneath those visible arrangements, there is a phase field whose gradients organize them, and K is our first clear letter for those gradients. Now let us return to the broader philosophical picture. There is a subtle but important philosophical shift here. In the usual picture, space is a neutral container, and patterns live inside it. Space itself is nothing except a stage. In the holophase picture, what we call space is the way phase differences are organized. K is not a decoration on top of space. It is part of what it means for space to have structure at all. Where K is zero everywhere, there is no spatial structure in phi. Where K varies, structure exists. You can think of K as the shape script of reality, the instructions for how phi's pattern is laid out. You, as a listener, are not outside that script. Your body, your room, your city, your planet are all phrases in the same spatial language. When you look at your hand, you are seeing an incredibly complex arrangement of matter, but underneath that, you are seeing the visible shadow of some deep phase pattern with a very intricate K field. We do not yet know the full details of that pattern. That is the work of physics and biology and many other sciences. But the holophase model suggests that there is, in principle, a single phase language that can describe it. Before we close part 13, let us tie K back into the larger tree of the holophase language. At the bottom of the master tree sits phi, the silent root, whose absolute value can be shifted without changing anything observable. In part 11, we honor that shift symmetry, the idea that only differences in phi matter. In part 12, we climbed the temporal branch and met omega, the rate at which phi turns as time passes. Now, in part 13, we have climbed the spatial branch and met k, the way phi varies across space. From k, higher spatial derivatives grow. Curvature tells us how the gradient itself bends. Divergence, spoken as the spreading or converging of k, tells us where patterns focus or fan out. Laplacians and other operators measure more subtle aspects of the weave. In later parts, we will climb that tower and see how forces, flows, and geometric effects emerge from those higher branches. But for now, it is enough that you can feel this. Whenever you see a pattern spread out in space, you are witnessing K in action. Whenever you notice that some regions are highly textured and others are smooth, you are noticing differences in the magnitude of K. Whenever you follow the direction along which a pattern changes fastest, you are intuitively tracing the arrow of K. In the next part, part 14, we will bring omega and K together in a single object called dphi, spelled dphi. Dphi answers the question, if I move a little in time and a little in space together, how does phi change? It is the first true spacetime letter in the holophase alphabet. From dphi, motion v will appear not as something extra, but as the choice of special paths along which phi stays constant. That will complete the picture we began in part 10, where we first met the triunity of time, space, and motion. For now, as you walk through your day, you can carry a very simple picture with you. Imagine that under every visible thing, there is an invisible fabric of phase. That fabric has a weave. Where the weave is tight, K is large. Where the weave is loose, K is small. You are a pattern in that weave. Every step you take, every glance you cast across a room, every view of mountains or buildings or clouds, is your nervous system reading the changing spatial pattern of phi. Salam and peace be upon you as we close part 13 of episode 6. We have stepped from the pulse of time into the weave of space and learned to name its first spatial letter, K. We have seen how K lives not only in equations and experiments, but also in your daily experience of patterns and textures. And we have reminded ourselves that behind this soft language stands a hard backbone of formal work, published and open to criticism, where K is defined, calculated, and tested. Our journey through the holophase language has only begun. The alphabet is just unfolding. In the parts ahead, we will keep climbing the master tree, one branch at a time, until the code of reality becomes as familiar to you as your own spoken tongue.